Today's speaker is Cayman Unterborn, and Cayman got his undergraduate and his PhD from Ohio State. His PhD was in geological sciences. He was then a postdoc and then an assistant research scientist at Arizona State. And he has now changed institutions to Southwest Research Institute in San Antonio. So whenever it is sane for him to physically move, he will be a mere 80 some miles to the south of us, and hopefully we can have much more frequent in-person interactions with him. I first met Cayman, I think it was a couple years ago at a Gordon Research Conference. And I was sort of immediately impressed by his breadth of knowledge and breadth of expertise. As I said, he got his PhD in geological sciences, but I think he is the most astrophysics literate geophysicist I have met yet. And he is going to show that in his talk today, which will be entitled A Matter of Time, the coupled role of stellar abundances, exoplanet radiogenic heat budgets, and climatic evolution. So take it away, Cayman.
Yeah, thank you. And well, I was first trained as an astrophysicist. I cut my teeth on Sloan Digital Sky Survey data. So yeah, thank you for having me. This talk is we've been working on it for a couple of years. My colleagues, Brad Foley, Steve Desch, Patrick Young, and a few others. Really trying to understand Earth, or what is an Earth-like planet. And I bring that up because my first slide, if I can get it to work, there we go, is, why do we care about Earth-like planets? And so I went right to the source and went to NASA and tried to find, what do they want us to do? And of course, their primary goal, I've got highlighted here, is to discover and characterize planetary systems, and specifically Earth-like planets around nearby stars. Now, Earth-like, I usually put that in quotes because it's a phrase that is near meaningless. However, I'll give you some examples of what Earth-like means to me as a geoscientist. So to me, Earth-like is not just something like mass and radius, it's actually fairly complex. It can be anything from, this is a mantle phase diagram for our Earth. So you can see it's rather complex with many different minerals, changing phase with depth and pressure and temperature, mantle convection, plate tectonics, these kinds of things, the structure of the planet, how carbon or water or your element of choice is cycled through the planet. And then not just that, but this is kind of the one that's a little bit more forgotten because it's a bit more sort of boots and hammer geology, but actually how that changes through time. So this is the geologic time periods, for the Earth. And of course, an exoplanet will go through this amount of time too. So it could have distinct geologic periods as well. Now on Earth, we have the luxury of lots and lots of data. So we have maps of the surface. We can actually look and see continents and oceanic crusts. We can see mid-ocean ridges to tell us there's something going on in the middle of the ocean. And of course that hints at plate tectonics. Perhaps most importantly, we have hand samples. We can go out and pick up a rock and learn something about the Earth's surface, parts of the mantle, and in some cases, the evolution of the Earth from very old rocks. Seismology, in this case, this is a picture of a tomographic map of the interior of the Earth. We can ultrasound our Earth and understand its structure, and then that can tell us about the physical and the pressure temperature conditions of these minerals. And then another great one is, of course, we have the meteoritic record. We can actually look and see what were the building blocks that went into the Earth and kind of weave together this story using all of these things. And of course, that's what Earth geoscience and planetary science have done for decades. Unfortunately, for exoplanets, we will have none of this. And so now I've called an Earth-like planet as kind of this blurry Earth. We are going to lack these observables. And in fact, I try to be liberal with what I considered an exoplanet observable, and it's really not that much. Planet mass, radius, if you're lucky, atmospheric composition, we'll know something about its current orbit. We'll know things about its host star, ideally composition. After this talk, hopefully age is added to that parameter as a common observable. Some more esoteric ones like albedo, if you have direct imaging, aurora, that, there's been a lot of talk about exoplanet magnetic fields. So this might be a new observable we can gain and what we can learn from that. So from those observables, you need to tell this complex story of an Earth-like planet in the context of not just Earth as in one Earth mass, one Earth radius, but the wide range of sizes we see for exoplanets. So things up to 5 Earth masses, where the pressure temperature space is much different than our own. Composition. So this is a lot of work I've done over the last few years of understanding how the range of stellar compositions can tell us about planet compositions. There's only one Earth composition, so understanding how these things change as you start changing something as simple as the magnesium to silicon ratio. We don't really know. Formation history, how things got to where they are, how they migrated. That means they formed in a different environment than they're at now. And that is a story through time that you need to know. And I think a really overlooked one is actually a core mantle segregation, where the core effectively sets the mantle's composition. And then from that, you set the crust composition, which sets the degassing parameter, so actually what kind of gases you're getting out. So it's for the Earth, this has taken over 4.5 billion years. For exoplanets, presumably these processes should still be happening. And now we also have the joy of there's hundreds of these things. So potentially hundreds of different histories. And this number rarely goes down, the number of exoplanets. So it's only going to get worse. And so how do we do this? This is kind of the really tough question of, given the observables we have, where should we even look for Earth-like planets? And to do that, let's first define, I think, a really critical conversation we need to have, which is, what does Earth-like mean? Or what is the bare minimum definition of Earth-like? And so for me, an Earth-like planet is really simply a dynamic one. And that means dynamic now, not sort of dynamic in the past. And so a great example of this is what we'll be talking about a lot today, is the carbon silicate cycle, or the carbon cycle. And it's fairly it's easy to understand in the abstract. So on the left here, we have sort of a cartoon of a plate tectonics carbon cycle, where you have material coming out at mid-ocean ridges. You have subduction bringing material back down into the mantle. Some of it escapes due to melting, comes back out at arc volcanoes. It's a relatively self-sustaining process. There's a whole other class of planets called stagnant lids, which I don't think it's too big of a leap to say are probably the most common type of planets, where you have a similar process where you have surface weathering, where you take carbon out of the atmosphere. It, through gravitational foundering, will drip back into the mantle, come back out, melt. You have other forms of degassing too. It's a much simpler process, but it effectively does the same thing as a plate tectonics planet, just maybe a little worse. And so that carbonate silicate cycle is really what, if you think about climatically, in the very simple sense, if you have too much carbon, if that process is just churning out too much carbon, you're degassing a lot and not weathering a lot, you might tip into a Venus. Whereas if you stop degassing altogether, if you are no longer a dynamic planet, your input of carbon to the atmosphere goes down and you're weathering it out, and you might actually be turning into a snowball. And so what we're going to be concentrating over here is this, which is when do planets stop being dynamic? Because I would say a planet that is not dynamic is not Earth-like, and maybe not worth our time observing for habitable exoplanets. So these processes are powered by, so basically the question we're going to ask is, what does it take to shut these things off? And this has been looked at before in some senses. So this is from work by Ed Kite a long time ago. It's really one of the first papers to explore this, looking at when volcanism stops on planets with large amounts of water on the surface. And he basically showed through really elegant geodynamics models that at about 50 oceans of water on a Earth-ish mass planet, so this is 50 oceans worth of mass on top, the pressure is so high, degassing can't happen. Degassing is both not just getting hot, but the pressure has to be low enough to have the phase change. Caro Dorn looked at this a couple years ago too, looking about the total amount of CO2 that gets pumped into an atmosphere as a function of time. And they found that at about 3-ish Earth masses, this degassing tends to stop. We won't come back to this, but our models kind of differ from theirs. But this idea has been in the zeitgeist of when degassing stops. What I think the critical step is that no one's really ever taken to is connecting it to the actual age of the system. So when I mean age and how we're going to tie this really complex process to age is, of course, that these carbonate silicate cycles are powered by heat. And so the heat you start with, in most cases, is the heat you're going to have, and it's going to diminish over time. Of course, the Earth is hot on the inside, it's cold on the outside. The heat will migrate from the interior to the surface. When the heat gets too low, then at that point, melting will stop. And so your planet will effectively stop. And so, of course, it's not just that every planet has an Earth-like heat budget, as I'll show. You could start with a small amount of heat. You could start with a lot of heat. And so how does this change the system? And this is particularly important when you look at this observable I've been talking about, which is host star age. So host star age is effectively a one-to-one proxy for planet age. They all form at roughly the same time. So on this plot, I've got on the y-axis host star age. So this is pulled from Exoplanet archive, and then planet mass up to about 6 Earth masses. So making a few cuts in this data set. So of course the mass, I only want to talk about rocky planets. We do have some low mass planets that seem to be low density and probably have lots of atmosphere on top. We're going to try to eliminate those by making a pretty conservative density cut of the density has to be higher than 5 grams per cc, which is not that bad. And then the other one, which I didn't actually really think of until late in the development of this paper, is those that have surface temperatures below the melting temperature of rock. So this kind of eliminates the Corot 7Bs that are basically magma ocean planets, because those could be young, but they're definitely not Earth-like for other reasons. And when you do those cuts, you have about 16 planets, including the TRAPPIST-1 planets down here. And so you can see kind of a wide variety of ages here. We've got quite a few that are younger than the Earth and quite a few that are older, and including the TRAPPIST-1 planets, which are actually what inspired this paper is that when the Burgesser and Mamajek came out with ages of 7.8 plus or minus 2, I think off the top of my head, it was like, that seems really old. I wonder if those planets are still active. So the heat sources for the planet, the battery that's going to drive these things, come in 4 parts. And there's some other stuff that is kind of negligible, but the 4 main parts: accretional heating. So this is just the heat of your formation when stuff hits you and you gain heat as you're forming. When the core segregates, you get a lot of heat that comes out due to gravitational energy. That is, so if you have a core, you have gravitational heat. The main one that can vary the most, because it's composition dependent, is your abundances of the radionuclides, uranium, thorium, and potassium. And that's what we're going to talk about today. And the last one is tidal heating. This can add an energy source to your planet, but not every planet, of course, is tidally heated. So that's why that one's in parentheses. So yeah, we're going to be talking about radionuclides. And so a quick primer on the radionuclides. Because it's not just how much you have, it depends on the half-life. So an element like thorium has a really long half-life. So it's kind of a really slow drip of energy. Uranium has 2 very different isotopes. 238 is 4.5 gigayears, and 235 is a speed demon at 0.7 gigayears. So this one burns really bright and fast. And potassium's kind of in the middle. It's got a low-ish medium half-life. And yeah, so, and then in terms of the power they produce, it's kind of 235 produces a lot of power per kilogram. And then it goes down to, let's see, it would be, yeah, you can see the kind of the order. Thorium doesn't do their, yeah, they're kind of all equal in that sense. So we were, a few years ago, as part of my PhD, we pointed out that there were stars that had very different thorium abundances. This was because it was kind of the easiest to measure at the time. And so this is for solar twins. So we actually minimized as much uncertainty as we could in the actual stellar abundances. We found that the sun is actually pretty depleted in thorium relative to silicon compared to a bunch of solar twins for its silicon abundance. And that was really interesting because we found this, some planets, stars and planets could have upwards of 200% more thorium than the sun. And let's see on the next slide. No, I didn't. Okay. So when you actually then, back in 2015, we didn't have the Hypatia catalog. And so in this updated work, we were actually able to use the Hypatia catalog to at least get a sense of what the other elements were doing. So thorium went from, I think we had 12 in our initial paper. Over the years, quite a few more have been added. And we're actually able to see this log normal distribution of thorium abundances, where our 95% confidence interval relative to the sun is between about 75% to about 200% of thorium abundances. Uranium shows a similar range. So in this case, we're using europium, which is a nucleosynthetic proxy for uranium. And you can actually show pretty easily that changes in uranium relative to magnesium is that you would show the same change in europium relative to magnesium. So for our purposes, this is fine. Potassium, on the other hand, is very interesting because actually it's formed by completely different processes than uranium and thorium, shows a very wide distribution of potential potassium abundances, 40 to almost 400% differences. So what we want to understand then is how these abundances changes the amount of radiogenic heat a planet might have. So we're going to look at it, as I mentioned before, for stagnant lids, and mainly because the Earth is the only planet we have with plate tectonics. We have a lot more examples of stagnant lids, and it's a bit of an Occam's razor argument. It's that it's probably more likely for planets to fall into stagnant lids, but that's a bit of an Earth-centric assumption as well. But actually, Francis Nemo wrote a great paper late last year that actually examined the plate tectonics end of this. So that's sort of the very generous end of planetary evolution. So I would recommend checking that paper out. So what we're going to do is we are going to create a model for stagnant lid evolution that Brad Foley created. I'm not going to spend too much time on what into it, but if you would like to know more about the model, we can go into it. The key things are that we include things like temperature dependent viscosity. We scale our planet with its mass and structure. We keep track of CO2 supply. We don't just keep the heat producing elements in the mantle, it can go into the crust. And we use a dry solidus. That'll come back later. Oh, as I say right there. So what we're going to do in our model is we're going to take a Monte Carlo approach, because unfortunately, not every planet or star has thorium, europium, and potassium measured. So we're basically going to randomly sample within these abundance distributions, scale them relative to the Earth. We're basically using these factors, since they're relative to the sun, as scaling factors to multiply by the Earth abundance. And then we have a few more critical things we have to take into account. So thorium and europium are both refractory, and that just means that their abundances roughly are reflected between star and planet. Potassium, on the other hand, has a bit more different of a story. The Earth only has about 20% of the sun's potassium content. So we have to take that into account. And we don't know if that's going to vary by planet to planet. We're going to explore that later, but we're going to keep it at 20% right now. And also, not every isotope of potassium is radioactive. Only a very, very small amount is. So this is also another unknown parameter. So we're going to pin it at the Earth and explore it later. So in terms of results, so this Q term right here is the heat produced, the initial heat production of that planet. So it's an initial heat budget total. Relative Q naught here is the Earth. Or no, this is a relative, in this case, this is relative to its own heat budget. And you can see that potassium can make up quite a bit of the heat budget, followed by 235 and then the other isotopes here. Now, if you were to compare the amount of heat produced relative to a planet that had the exact same amount as an Earth-like planet, so all of these scaling factors being 1, you can see quite a bit of difference. You can see things down to half the Earth's an Earth-like heat budget, all the way up to 3. So quite a wide range of initial heat budgets. Now, in terms of degassing, we take these models and plug it into, so this is kind of the how this system will work. So on the x-axis here, we have time, and then on the y-axis, we have degassing rate. So you could really, the dashed curve is the one we care about. So initially, you have this really high spike in degassing rate, and then the planet's evolving, cooling down, and eventually the degassing rate falls to 0. And at that point, we say, you are no longer a dynamic planet, we're throwing you out. And then I want to know that age. and then you can track surface temperature as well. But I unfortunately won't get too much into the climate aspect, but more of just age is kind of our proxy for climate in this case. So the kind of questions we're going to be asking is, how old is a planet when it starts and ends degassing? What controls this lifetime? And I won't have time to get into supply limited, but if there are questions on that, I can talk about it. Oh, right. So there we go. That's the real big question is, how old is too old to be Earth-like? So here are our results. Really, we kind of break our degassing lifetime into three components. The start time, so how long does it take for the planet to sort of get hot enough to actually begin melting, how long that lasts, and then sort of start plus duration gives you the age when degassing ends. And so on the x-axis for all of these is mass. In general, you can see that as a planet gets more massive, it degasses for longer. There's also quite a wide range in both start time, duration, and the age when degassing ends. Right. Now, if we dig into what parameters are controlling this, it really falls down to three parameters. This first slide is degassing start time on the y-axis for all of them. We've got heat production, viscosity, and initial mantle temperature for a 1 and 6 Earth mass planet. And they look fairly similar, that if you have a low heat budget, you tend to degas later. However, if you have a higher reference viscosity, you always tend to start later. And if you're cold, you also tend to start later. That kind of all makes sense. There's really nothing surprising in that. Now, when you look at duration, things get a little different. The initial mantle temperature completely goes away. It's almost completely insensitive to this. And I should say there are about 200 or 300,000 models in these plots. Viscosity, you can see a weak dependence. It's still there, a dependence on reference viscosity on the duration of degassing. But you see a very strong dependence on heat budget from radionuclides affecting the degassing lifetime. Of course, it's a bit more complex than this. So looking then at only reference viscosity and heat, which is this plot. So on the x-axis here, we have reference viscosity. On the y-axis, we have this heat budget relative to an Earth-like planet. The white lines represent the 95% confidence intervals for the heat budgets. The black lines represent rough estimates of the 95% confidence intervals of degassing lifetime. And this is going to be really important. So anything up here, these really long degassing lifetimes are actually relatively rare. But coming back to the two parameters, you can kind of see that as viscosity increases, of course, degassing lifetime increases, and you don't need as much heat to get that long degassing lifetime. So this viscosity kind of slows everything down, but never slows it down enough to make melting stop altogether. And the difference between a 1 and 6 Earth mass planet aren't really all that different, except the 6 Earth mass planets degas longer, like we expected. If you were now to break it down by radionuclide, things get even more interesting. This is a lot of plots, so let's just look at the left one. This is really just a 1 Earth mass and a 6 Earth mass. So on this, now I've got degassing lifetime versus the amount of heat produced relative to an Earth-like planet for that element. So like I said, it's unfortunately very complex. And the color coding here is the reference viscosity. And you can see kind of pretty clearly that it's relatively insensitive to thorium, slightly insensitive to 235, ever so slightly sensitive to 238, but potassium for low viscosities below about 10 to the 21, which is about an Earth-like reference viscosity, it's fairly linear. More potassium means more degassing lifetime. Things get muddy, of course, with higher viscosity, where yeah, things can get weird. So in order to sort of disentangle all of these parameters, Brad Foley had a really great idea to basically ask this question is, okay, for a given planet, what's the minimum temperature and then heat budget you need to produce that temperature to have melting? Because that will tell you is what's the bare minimum threshold you need to meet regardless of your radionuclide heat budget. Because you could have a lot of 235 and melt really quickly, but die out super young. Or you could have, I don't know, massive amounts of thorium, which just churns along slowly, maintain that temperature for a very long time, and be able to melt. I'm not going to spend too much time on this. This basically shows here's the temperatures as a function of mass and viscosity. Here's the heat budgets. What I really want to get into is the individual elements. So here is now the age when degassing ends versus reference viscosity and this is the amount of heat from one isotope it takes to produce that degassing lifetime. And the contours are that, of course, relative to this Earth-like. The band here is our 95% confidence intervals, again, from our model. But in general, that as degassing lifetime gets really high, you need lots and lots of potassium to do that. In the thorium case, is this thorium? Yeah, thorium. It really doesn't take that much, like only about 3 times an Earth-like amount of potassium to do it. Now, say you have really low viscosity, of course you need 6. And then the same for 238. 235 is very interesting, again, because it has such a short half-life. You need almost 20 times the amount of 235 as the Earth has to get that abundance. For 6 Earth mass, it looks very similar. Everything kind of gets, because degassing times are longer, thorium and 238 become much more important, but I'll show that in the next slide. But of course, let me actually go back. These are independent, these model results of how much potassium, thorium, uranium you need are basically just a parameter search for these. We know from the stellar abundances that there is a distribution of these things. So while 20 times, you do need 25 times uranium 235 to get that heat budget, those are actually exceedingly rare. So we can now transform this into a plot that shows, and again, let's only look at the left one. This is the probability that your planet inherits that much potassium, thorium, or uranium. So in general, you can kind of see that, again, age, degassing lifetime on X, reference viscosity on Y, potassium, you have about a 10% chance of getting that much potassium, which is pretty good, or you have a fairly high probability relative to the other ones. So in this case, thorium, your probability gets exceedingly low, except at high viscosities, which is interesting. At high viscosities, because the degassing lifetime gets so long, potassium can't support it anymore, and a long-lived radionuclide has to pick up the slack. So in this case, thorium would be more probable to do it. Uranium 238 is similar to thorium, and of course 235, the probability of having that much 235 is exceedingly low. For 6 Earth mass planets, it becomes very similar story, except now for these high viscosity long degassing lifetimes, you actually need a lot of thorium and uranium 238 to do that, mainly because of their longer longer half-lives. So now we can go back to this plot and actually kind of map onto it what we're looking at in terms of probability of actually having that degassing lifetime. So outside of the 95 confidence percent intervals, it can happen, it's just really rare. But for the average exoplanet, potassium is going to be the element that controls your degassing lifetime. Viscosity will change things, but you still need a nominal amount or a super nominal amount of potassium to make that degassing lifetime happen. For larger mass planets where degassing lifetimes get long, 238 and 235 do need to support the degassing lifetime. So you do need now a super Earth, a larger amount than the Earth and Sun to do it. But these are kind of uncommon. And then of course, these really rare degassing lifetimes, you would need lots and lots of 238, 235. But we can measure that. And of course, so I think everything in exoplanets gets a wacky name. So I decided to call these potassium-rich planets banana planets. And so, yeah, I call these banana planets. So, moving on, getting back to the question at hand, which is how old is too old? Again, on the y-axis here, we've got age and mass, and these are our 16 exoplanets. Combined with our degassing lifetime, we can then ask that question. Well, if I'm really old, but I degas for a really long time, I might actually still be degassing. And of course, young stars may not have enough energy to degas. So would they still be degassing today? And so we can combine these two. Now, but we actually have a critical assumption that I vaguely mentioned earlier at the beginning, that the way we scale these planets is scaling it relative to the Earth and the Earth's current abundances. That is unfortunately not true, because the abundances of these radionuclides have not been stagnant through time. They've been produced at different rates through supernovae or stellar evolution. And we had different amounts at the beginning of the galaxy's birth to now. And so our abundances we were using before are abundances that are only valid for 4.5 billion years ago. So Elizabeth Frank and colleagues a few years ago actually realized this and sort of modeled this for the solar annulus, and showed as a function of time of formation, which is on the x-axis, the mantle concentrations of the radionuclides have changed through time. For potassium, it has gone up and then has slowly started going down. For the others, they have basically been decreasing throughout galactic time. Now, abundance, of course, doesn't translate to an actual amount of heat produced. And so what's interesting here is that very early in the galaxy's lifetime, uranium-235 actually produced a lot of a planet's heat budget, with only at about 5 billion years after galactic birth, the birth of the Milky Way, did potassium take over. So that's really interesting. So effectively now, if we really wanted to ask how old is too old, we need to take this galactic chemical evolution into account. Now, this only works for the solar annulus, so there, of course, can be, again, system-to-system variation. So we're going to combine these models, and instead of using the Earth abundances, we're going to use these abundances, or these at least scaling them system to system, run our Monte Carlo again, and now we can produce plots that are the time of planet formation versus mass, and your color here is your degassing duration. So I have the average is in the middle, the lower end of the 95% confidence interval and the upper bound of the 95% confidence interval. So looking at the average, you can see that older planets, if you were born very early, like 2 billion years here, you can have a very long degassing lifetime, almost 4 billion years, if you're high mass. As you creep over to when potassium dominates, it gets a little, the degassing times go down and the dependence on mass goes away too. At the upper end of our degassing lifetime, which is really what we care about, we really want to push age to its limits, degassing lifetimes upwards of 8 billion years for these really old stars. Now, of course, you may have realized that the galaxy is 12.5 billion years old, but these are only degassing for 8 billion years. While they degass for a very long time, they do not degas, they are not degassing today. So we can actually turn this into, oops, that's an old plot. We can actually turn this into, now we're going to take age and mass, and actually the colors here are the critical age at which you would expect degassing today. So in this sense, really old planets degas for a long time, but they aren't degassing today. So this line represents, if you're above this line, you're likely degassing today. If you're below this line, you might be degassing today, but odds are you won't, and might actually aren't and fall into a snowball. Our average is between about 2 and 3 billion years old here. If you are unfortunate and have a very low potassium abundance, you are not degassing today. In the high viscosity cases and lots of uranium and thorium, you can push this to maybe 5 to 6 billion years, at least for this model. So now, if you're an observer and you ask me, is this planet too old? I can actually assign a probability. So these are the probabilities. The colors here is the probability that you are below age crit, taking into account the uncertainties in mass and age. And you can see there's only 2 planets that have above 2 sigma 95% likelihood to be young enough to be degassing today, and it's K236b and Kepler 80e. Now, if you're a little bit more liberal and use the 95% confidence interval, you get quite a few more, only about 4 or 5 that are above the 95% confidence interval. However, this may only be valid for very massive planets, not these really low mass planets. So this is only helpful in some ways. But by plotting a planet, if you measure its mass and its age on this diagram, you can actually get some sense of what to expect climatically. And so, yeah, so again, right. So a lot of that previous plot comes down to the slope of this line, where this line falls is dependent on potassium, as we talk about in this plot here. Now, again, coming back to what I mentioned before is that potassium is a moderately volatile. So in these models, we assume that every planet has 20% of their complement of whatever the star is, and that the potassium 40 to total potassium ratio is the same. These can vary, and we don't know how much they vary. So we can actually model that. So this is, now we are going to be running those same models, but we're gonna essentially induce fractionation or volatilization of potassium, or increasing or decreasing the potassium 40 ratio. They do the same things, and show how these critical ages change when you have, say, twice as much volatilization and you get half as much as the Earth. So this would be 10%, and this would, or twice as much, you actually now get 40%. And you can see age crit can actually move down quite a bit, almost 2 billion years, almost adds another billion years to the endpoints of age crit degassing. On the 95% confidence interval, it does a little bit, especially on the halving end. So if you have too low, you eliminate a few planets, you move that line up considerably. It doesn't do much on the high end because viscosity is really actually dominating here, not potassium. So that's really interesting too, and shows kind of a really critical thing we need to get our brains around. There are other things that matter too. So plate tectonics, as Francis Nemo and others have shown, can extend this degassing lifetime indefinitely. Maybe not indefinitely, but a very long time. The Earth is still degassing. Tidal heating can, of course, add more heat and change things. Water, I get asked this a lot, and it's actually not as straightforward. So water is very interesting because it can lower the melting temperature of rock, which makes it easier to degas. However, it can also speed up a lot. It lowers viscosity. So you have this trade-off of lower viscosity could mean lower degassing lifetimes. Water can then decrease the solidus. So it's really complex. And Brad and I are working on that now, and others have worked on it for plate tectonics. But it's an open question of whether it will increase or decrease or not change age crit all that much. If you have both, of course, you're going to have a longer degassing lifetime, or I guess all three, maybe. But an interesting question comes out of this, which is if you have a very old planet and you can figure out what you're looking at active degassing, and you can eliminate tidal heating, that may actually be a signal that you're looking at a planet with plate tectonics. And that's really cool. I don't know what a signal of active degassing is, but it may be one way to use age to actually tell whether you should be looking at plate tectonics, because the only way it could be degassing that long, according to our models, is plate tectonics. So I want to end with some open questions and how to tell if your planet is Earth-like. So for the observer, things we would really love is stellar ages. And I know that is a fraught field, but uncertainties on the order of 2 gigayears might be okay, just understanding where we need to plot it on that diagram. We really need to know masses because, as I've shown, it's kind of very sensitive to the mass of the planet. But if you have an old and massive planet and you measure that there's 2 to 3 times the amount of solar uranium and thorium, or europium and thorium, you might be seeing a planet that can degas. If you're young, you really need to ask the question of how much potassium you have. I'll quickly go through these open problems. We need to understand viscosity as it changes with mass and composition. Carbon sequestration is going to matter a lot. For astronomy, host star radionuclide abundances are key. Thorium is the hardest element in that, and it's slightly hard. Uranium is impossible, but europium works. We really need to understand the galactic chemical evolution of this ratio. And then, for meteoritics, the amount of potassium depletion, as it, is huge. We need to understand if this 20% depletion is normal for the Earth and for other planets, or if we have a lot, and that's just how we formed. So I'll end with this. The key point here is Earth-like planets are dynamic planets. I really would like to, and dynamic today, not dynamic in the past. And that's mainly for climatic reasons. There could be other things that go on that can push you out of a snowball, but it's pretty tough to do without an input of carbon to the surface that is fast enough. Yeah, yeah, I think that's it. You can read the rest, and I've stated the rest. But yeah, thank you very much.
Okay, well, thank you, Cayman, for a very interesting talk. And I know that it certainly got me thinking about a lot of things. I think we have a small enough group that if people have questions, they can just go ahead and ask them. But I'll ask a first question here.
Sure.
You discussed to some extent the galactic evolution aspects of all this, but when you were looking at properties of stars and stellar abundances in general and going into the Hypatia catalog, were you looking at solar type stars, i.e. thin disk stars, or were you looking at the entire ensemble of stars in there?
So that would be I basically pulled Hypatia. So
Mhm.
FGK stars is kind of the only, excuse me, the only it is the only cut in the data set. And
Okay.
that's, so yes, that would be another very interesting thing is um where you form can actually inform your abundances of these. And
Yeah, so you weren't trying to cut on kinematics or overall abundance ratios other than overall metallicity and whatnot. Yeah.
exactly, yeah, we
Mhm.
really tried to do our best to be as because we make a lot of assumptions throughout and didn't really have the ideal data set for this. We just wanted to run the parameter search
Yeah.
to figure out which were most important. And then I think in the future, yeah, it's doing those kinds of cuts
Mhm. Yeah,
to
because
really
that's one
understand.
aspect I'm extremely interested in.
Yeah.
Okay, do other people have some questions?
I have a quick question. Hi, Cayman. That was a great talk. Um, my question is on how much volatile material there actually is to degas, especially for some of these that have really long degassing lifetimes. Like, can you do like at least a back of the envelope calculation of like how much material is degassed, and does that match how much volatiles a planet would be born
Yes,
with?
I can. So this is the stuff I didn't get a chance to talk about. So a planet almost always will degas most of its carbon fairly quickly. And so then it comes basically down to how fast it can set up a recycling system to, actually, let me go back. So in this case, this is the other example. So this isn't a snowball. This is a planet that can degas for as long as you want. But if the energy budgets and its carbon abundances are too high, so this orange line I didn't talk about in the last figure is the supply limit. So if your degassing lifetime ever falls above this line, you basically have tipped into a hothouse Venus-like regime because you've overwhelmed the weathering rate and it's a runaway. So it's right. So now you can ask, how much carbon do I need? And unfortunately, these are in geoscientist units, so I'll walk you through it. How much carbon do you need to actually not overwhelm your system? So that's kind of a version of the question you asked, since most of it gets degassed. And essentially, so let's look relative to the Earth, so I don't have to explain weight percent carbon in a mantle. For low mass planets, it's actually, you can't have a lot of carbon, less than the Earth's amount of carbon to do this. And this is actually really surprising because the Earth has an Earth-like amount of carbon, but we didn't fall into a hothouse. As planets gets more massive, this actually gets, you need even less amount of, a lower amount of carbon will produce a supply limit. So these really massive planets actually can't form with a lot of carbon, otherwise things can get dicey. And that's similar to the water problem that Ed Kite and I have talked about, that too much water is actually a bad thing. So you need not just dry planets, you need relatively carbon poor. But the Earth does pretty well with low amounts of carbon. So 10 times more carbon than the Earth is actually maybe already bad in a bunch of other ways. Did that answer your question?
Yes, I think so. It's complicated. I have to wrap my head around this picture, but yeah.
Yeah. The planet will do its best to spit out its volatiles because they're not compatible in the melt. So it just goes to gas. However, so the interesting aspect of that is if the core gobbles up carbon during formation. So you could start with a lot of carbon that you inherited on formation, but your core takes a lot of it down, you might end up with a mantle that's perfectly fine with having a temperate climate.
Okay, do we have further questions from anybody?
Yeah, I have one. That was a fantastic talk, Cayman.
Thanks.
My question would be, so we didn't really talk about whether magnetic fields matter, and obviously it's not an observable, but I'm just
Yep.
curious, where that is in this equation of the ability to hang on to an atmosphere, the degassed components.
Yeah, and in some sense, we don't care.
Right. Okay.
It's because it's sort of it's a 0 or a 1 in the sense. Are you degassing or are you not? So in the magnetic field might matter more for these planets that can tip into a hothouse, where you actually need to get rid of carbon to maybe tip back into a temperate. I guess on the other end for the snowball planet is it may, if you're losing carbon to the magnetic field, to a lack of a magnetic field, that would certainly lower the amount of supply you can weather into rocks. And so you actually might hit a snowball earlier, I would say, because your carbon budget is now so really what these models are showing is that the degassing rate out of the mantle matters kind of the most. The weathering rate matters too. But if you give that degassing rate less to work with, you're effectively lowering the degassing rate. So yeah, I mean, a magnetic field won't change the lifetime of degassing, except for the worse if you don't have one.
Cool.
Okay, other questions?
Hi, Cayman. This is Chen. Sorry, I have a very noisy background. My son is taking a class. I missed the first half of your talk, but I think this is a very, very good talk. I have a question on the degassing process you were talking about. Seems to me the degassing process or degassing rate you're talking about is equivalent to the amount of magma or magmatic flux, right?
Yes, and it is dependent on that, yes.
So essentially, this degassing process is different from the petrological degassing process, like usually geochemists talking about. Like degassing from the magma depends on pressure, temperature, redox condition, and many other parameters. But I think to the first order, looking at the magmatic eruption flux, it's a very, very, I don't know, more like a tangible parameter to quantify. But in terms of the real pathological degassing process, maybe another process could potentially incorporate in your model later on, because
so that is actually incled in
really?
this. So
sorry.
Yeah, it's I understand it only nominally, and so I often gloss over it and only look at the total degassing rate. But we do include a metamorphic degassing rate at the surface, so it never interacts with the mantle. And so the black curve is the only mantle degassing, and the dashed curve is mantle plus metamorphic. So the metamorphic, yeah, is non-trivial. And of course, that is now dependent on your crust composition, which is definitely not a part of this model. I forget how Brad did it exactly. I think there is some compositional aspects in this, but not much. So yes, your metamorphic degassing rate is also critically important and should definitely be explored more.
Thanks.
Yeah.
Okay, further questions for Cayman?
I guess I'll throw in more out there.
Okay.
So we have the internally generated degassing, right? But you could envision a system of a higher impact flux where that's your other way of devolatilization and degassing. Of course, that has its own problems as well. But I just wonder if that thought has been modeled at all.
I know people have looked at erosion of primordial atmospheres from impacts. I don't know about total rate, and I mean, so it's a double-edged sword.
Right.
You will have more heat. You'll probably lose some atmosphere in the process, but you also will then degas that to your primordial atmosphere, and whether you can in-gas it back in or it just stays there, and then that will actually probably change your evolution, because now you kind of have a thermal blanket around your magma ocean. So in some sense, these models kind of have a very idyllic case, which is you have nothing on top at the end of your magma ocean. You've solidified, and now normal melting starts. But the early Earth, or the early exoplanet magma ocean transition to solid, it is pretty important and probably will affect these results. I have trouble seeing how it will increase that critical age, though. In some sense, I would imagine that I've tried my hardest, and there are a few parameters that can increase age crit, like they're like by 500 million years. It's not that much, but essentially getting planets like TRAPPIST-1, which are supposedly very old, getting them to be actively degassing today without plate tectonics or tidal heating seems really hard. However, by framing it in this context of an observable this age, I think it gives, especially geoscientist modelers, a different way to think about it, of kind of really the only parameter we care about, at least for this, if this, then that, or 1 or 0 kind of modeling. For atmospheric modeling, of course, that makes a big difference. But I think in terms of 0th order parameters, where should we be looking? How the magma ocean phase affects the lifetime of degassing is probably a simple question that is not often asked.
Okay, great. Anyone else have a last question for Cayman? Well, let's all thank Cayman for a really thought-provoking and excellent talk. So that was great. So thanks a lot, Cayman.
Thank you.
Excellent.
Thank you, Cayman.
Thank you.
Thank you.